Okay, we'll start a new topic today. I'll cover a small part today and I mean the so this is not included in the exam tomorrow, but this is an important topic. So I'll start it and of course there will be a lot more discussion after tomorrow's test. Okay, so this topic is called process synchronization and this is a very important topic in operating systems. So for this we are using Galvin's slides because the slides are very good. Okay, so let's start. So till now we have understood that many processes are executing concurrently in a computer system, at least in a modern computer system. So a particular process may be interrupted at any time due to context switch. So it might well be that a process has completed up to a certain point or has executed up to a certain point, and then there comes a context switch. So some other process will be allocated to the CPU, and this process which was running, this will be kind of shifted out. And we have discussed this, like its context needs to be saved. So there is some overhead and so on. But for example, by now we understand that a process does not execute at once from start to end. Rather, it may be given different time quantums and it will execute partially during each time quantum. So maybe a process will finally get 100 time quantums. Right? So for some time quantums, it will execute a particular part of the program. And then maybe it will go into IO. So it will not be in the ready queue. Then after IO is completed, it will come back to the ready queue and then it may be given another time quantum and so on. Now we have also discussed shared data. That means we have discussed shared memory. So now think about it that suppose multiple processes let's talk about two processes for now. So say two processes have some shared data and they are accessing that shared data. Both are updating or reading and so on. Now, the concurrent access to shared data may result in data inconsistency. We will soon take an example and understand why. So this is the main problem, that concurrent access to shared data may result in data inconsistency. And maintaining data consistency requires some mechanisms, which are called process synchronization mechanisms. That is what we are going to study now. So first of all, let us understand why is there at all a problem? Right? Why should data inconsistency arise? So for that, let us go back to this producer-consumer problem that we discussed about, I think, 3 weeks back. So if you remember, there is a producer which produces new items and a consumer which reads those items. And there is a buffer. So we assumed a bounded buffer. And if you remember, we discussed things like the buffer is being treated like a circular queue and stuff like that. And in a particular scheme, we said that. Okay, Ramnivash is asking here by process, we don't mean threads. Yes, we are meaning processes. However, the same problems apply to threads also. Like there is a similar concept of thread synchronization. Of course, threads, like you might think that threads do not need shared memory, but still, let me demonstrate the problem. You will understand that threads also might run into this problem unless they are properly synchronized. Okay. So if you remember, we discussed that producer consumer problem where we discussed a particular scheme where we would be able to use all slots in the buffer. And in that scheme, we said there would be a shared variable counter. This is shared between the producer and the consumer. So counter is initially set to 0. It is incremented by the producer after it produces a new item in the buffer. And this counter is decremented by the consumer after it consumes a buffer or consumes an item from the buffer. So just as a recap, this is what we discussed earlier. This is the code for the producer. So it produces an item and then it checks if the buffer is full. So as long as counter is equal to buffer size, that means the buffer is full. So it should wait. The producer should wait. It should not try to push new items in the buffer because the buffer is full. Once counter reduces, like it is no longer equal to buffer size, then it can push in the new element in the buffer. And then it does this. So this is the pointer, if you remember. So this in pointer is pointing to where the producer will push the new item. And then this is what it does, counter plus plus. Okay, this step is important for us. So that's why it's marked in red. We will soon understand why. So this is what it does, counter plus plus. Remember, counter is this shared variable between the producer and the consumer. Similarly, what does the consumer do? It first checks whether counter equal to 0, and as long as counter equal to 0, that means the buffer is empty, the consumer has to wait. When there is some valid item in the buffer, then it consumes it, and then it increments this pointer out equals to out plus 1 modulo buffer size. So we discussed this, that we are treating this buffer like a circular queue, and therefore this modulo buffer size and so on. So out is that pointer which says from where should the consumer read the next item, right? And then the consumer does counter minus minus. Okay. So this counter variable is shared between the producer and the consumer. So producer is incrementing it and consumer is reducing it or decrementing it. Now, the important thing to understand here is that, say this kind of a statement, right, in C, say in C program or some high level programming language like C, Python, etc. We write this kind of a statement, counter minus minus. Now you all have done a compiler course, so you have some basic idea of possibly how assembly language looks like. How do you think this statement would look in assembly language? So finally, the program would be translated into assembly code, right? And then finally to machine code. So how do you think this instruction would look like in assembly code? So counter plus plus or counter minus minus. So the first question is, okay, Abhishek says reg equals to reg plus 1. But what is in reg? So let me ask a related question. Yeah, so but Abhishek, I mean, how will that happen? As in, you have to do it, right? So the thing is, this counter plus plus or counter minus minus. We write this one statement in a high level language. But when it gets translated to assembly language, will it be one instruction only or a set of assembly language instructions? Exactly what Sriharsh and Dhrumilis are saying. So counter must be loaded from the memory to some register and then decremented or increment. That register should be decremented and incremented. And then that changed value in the register should be stored back to counter. Okay. So exactly what you all said, like including Shomnath. The single statement counter plus plus, which we write in a high level language, will actually get down to possibly these three instructions in the assembly language. So first, the count, this thing would be loaded into a register, say R1, and then one would be added to it, and then the changed value would be stored into R1. I mean, would be stored into this location count. This is what the producer will do, counter plus plus, these three instructions. What will counter minus minus do? This is the consumer. Again, this will be these three instructions. So the important point to note here is that what we write as a single statement in a high level language can actually be translated to multiple instructions in an assembly language. or machine language. And therein lies the problem. Think about it, what is written in the lower part of the slide. Consider an execution of this producer and the consumer where count equal to 5 initially. The producer executes this line, register equal to 1 equal to counter. So this load instruction say the producer executes. And then it executes this one. It's add I instruction. But then there is a context switch. Okay, so the producer is shifted out of the CPU and the consumer is allotted the CPU. So now the consumer starts executing and it executes this instruction, load R2 count. What value of count will it see? The problem is that the producer incremented the value in its register, but it was not able to write back that increased value into the location of count. It got swapped out of the CPU before that. And the CPU was allocated to the consumer. So now when the consumer again executes its load instruction, it will see the older value of count, which is 5. The consumer will have no idea that the producer was incrementing this value of count. So now let's say the consumer executes this sub instruction. So now what's the idea? Now the result is that in the register, in the register 1, according to the producer, the value is 6 because it has incremented the value of count by 1. But for the consumer, the value in its register is 4 because it has decremented the value of the counter. So now let's say again there is a context switch and the producer executes this store instruction. Right, so this step, producer executes this step, which is analogous to this store instruction. So now the counter value, the 6 value will be returned to counter. And then maybe another consumer executes. The consumer again is given the CPU. It executes this instruction, which is analogous to this store instruction. So then the value of counter again becomes 4. Okay. So this is the problem which can arise. This is why data can become inconsistent because multiple processes are executing concurrently. So basically 2 reasons. One, multiple processes are executing concurrently and they are all accessing the shared variable. Second reason is that what we write as a single statement in a high-level language actually gets translated into multiple such instructions in assembly language or machine language. And we cannot guarantee that between 2 instructions, a process will not be swapped out. And when exactly a process is swapped out, that is not in our control or not in control of the process. So this is how shared data can become inconsistent. Is the situation clear or any questions? This is the key point of this lecture, as in one of the key points, like what is the problem? Then we will discuss several ways of handling the problem, but you need to understand the problem in order for this chapter to make sense. So any questions about this? Okay, let me proceed. So what we understand is that concurrent execution of, so similarly, like concurrent execution of parent process and child process may also result in race conditions. In fact, concurrent execution of threads may also result in race conditions. And so what is a race condition? We will use this term often. A race condition is a condition where the outcome of execution depends on the exact order in which the instructions, which can be spread over multiple processes, get executed. Right? So exactly what we saw in the previous slide. Let me go back. This is a race condition. Here the final value of the counter depends on the exact order in which these instructions ran. So there are 6 instructions, right? So the exact order in which these 6 instructions will run, that will decide the value of counter. And it is kind of non-deterministic, as in different uh, different orders of execution can lead to count to have different values. So here also in these last 2 steps, if I reverse these 2 steps like these two, if I reverse the order of these 2 steps, counter will end up with the value 6, not 4. Okay. So this is the situation where the final value of a variable or a memory location can depend upon the exact ordering of different instructions, which are spread across different processes. So within a particular process, you can be reasonably sure that instructions will execute in order. Though nowadays, I think from your core knowledge, you know that uh, because of pipelining, etc., there is sometimes out of order execution. Right. So some instructions which do not, like some instructions which depend upon a previous stage in the pipeline may be actually pushed back, etc. But anyway, like those the compiler handles. But in general, you can assume that in a like logically in the same process, instructions will proceed in the same order in which you have written. But no such assumption can hold, or no such assumption should be made about instructions which are in different processes, and that can lead to a race condition. Okay. So this whole chapter is about process synchronization, which is how to avoid race conditions. Okay, this is a very common situation where multiple processes or multiple threads are updating the same shared variable. So if we do not take any steps to prevent race conditions, they can easily occur. So you have to take some steps. And those steps are called process synchronization mechanisms. So more formally, this problem is called a critical section problem. So consider a system of n processes. Like in our simple example, it was just 2, but just for generalizability, consider a system of n cooperating processes. Each process has a section of code which is called the critical section. And in this critical section, the process would be modifying shared data, which might mean updating common variables, updating shared table, writing a file which different processes are accessing, and so on. Right, so the name is intuitive. Critical section means it is doing some steps which are critical. That means which can result in race conditions unless we guard against it. So what is the basic requirement now for process synchronization is what is written in red here. While one process is executing in its critical section, no other process is allowed to execute in its critical section. Okay, and the critical section problem is to design a protocol to solve this. So any questions here? If not, I have a question. Okay, let me ask my question. Focus on the lines which are written in red here, these lines. So what does this line even mean? Because right from the beginning of the course, we have been saying that we will focus on a uniprocessor system where only one process can execute at a time. So what does this even mean? While one process is executing in its critical section, no other process is allowed to execute. Like when one process is executing in its critical section, why should we worry about some other process executing at all? So what does this mean? What is the idea here? I hope my question is clear. We are still assuming a uniprocessor system. Then what does this line at all mean? Why are we even worried that if one process is executing in its critical section, some other process can execute? Why are we even worried about this? Okay, Aryaman and Srihash are telling basically the same thing, or even Mayank, that context switching should not happen. That as long as a process is, okay. So let me see. So Aryaman, Srihash, Mayank, yeah, all are telling the same thing, that the process should not, I mean, as long as the process is executing its critical section, it should not be swapped out, or there should not be any context switch. Okay, that's a possibility, but that's not very practical because a critical section can also be quite long. Maybe a big shared table needs to be updated. Right, so if you have this restriction that as long as one process is executing in its critical section, there will be no context switch, that will be a very inefficient design. So actually it does not mean that. Okay. What it means is what some others are saying. So I think, yeah, Shubham kind of hinted about it. Then, okay, Ramnivas also said the same thing, but I'm saying that this is not the actual idea. Like, yeah, one simplistic idea can be that as long as one process is executing in its critical section, there will be no context switch. But that's typically not a good design because the critical section can also be quite long. Right, so the whole idea of multi-programming will be defeated if you allow one process to execute for so long without context switch. So that is not a very efficient design. What is meant is what Vij pointed out. Right. So let me try to explain this. Let me see what the others are telling. Okay, Tanmay has a question which I am not understanding. Wait, in its critical section, where? Okay, when one process is in here, here it means the process after context switch or the running process. No, it means the running process. So one process is executing in its critical section. I mean, we're talking about the running process itself. Okay, and show. Okay. I'll come back to the question I asked because it's important to understand. But I see some of you have some doubts. Soumitra is asking, but the current running process can't access the shared data of the critical section of the previous process. Why not? The data is shared, right? So Soumitra, can you unmute yourself?
Yes, sir. Sir, I have I have two comments. Previous I have commented means this is in addition to that answer. Actually, it is in my hand.
Okay, so tell me what you are telling.
Sir, that means suppose a process has entered the critical section. After that, it is not completed. It is not exited from its critical section. In this case, the process is the context switch happens. And a new process is and another process is running in the CPU, then the running process can't access means program should be such like that it should not access the shared data of that critical section of that program.
Okay, so you are not asking a question, you are commenting. Like,
Yes, sir.
you're trying to explain what I asked.
Yes, sir.
Yeah, okay, yes, you are in the right track. Okay. So, okay, you can mute yourself again. Thank you. Any other comments? Yeah, so actually what Vij also pointed out and what Soumitra also said, let me now explain. Or Abhishek, yeah, Abhishek also said. So let me now explain. So it's clear that one process is only executing at a time. But let's talk about two processes, PI and PJ. So suppose PI started executing its critical section. Before it finished executing its critical section, it was swapped out and PJ was allocated the CPU. Now PJ also has the same shared memory. So now PJ is running, but even then it should not be allowed to access that shared memory, which it shares with PI because PI is in its critical section. Okay. So PI, let me repeat, PI is executing in its critical section. Maybe it is in the midst of updating shared variables, etc. But in the midst of it, it was swept out. So one situation could have been what some of you commented, we will not allow that context switch as long as the process is in critical section, but that is a very inefficient handling. So we will allow context switches, but with this restriction that even if PI was shifted out, or PI was context switch happened and PI was removed from the CPU, PJ was allocated the CPU. Even then, PJ will not be allowed to access the variables, the shared variables, which it shares with PI, because PI was in its critical section. So basically, PI will have to give some indication that I am starting my critical section. And then even if it was swapped out and PJ is allocated the CPU, PJ should check whether PI was in its critical section. If yes, it should not try to access those shared variables, etc. Okay, this is what this means. It does not mean that two processes are executing simultaneously. It's still concurrent, but like before PJ tries to access its critical section, there should be some mechanism so that it can check whether PI had started its critical section. If yes, PJ should not start its critical section. Is it okay? Again, this is an important point to understand. So if you have any queries, then write here. Okay, if there are no more questions, I hope this point is clear, because yeah, this is the crux of what we are going to discuss. Okay, so the typical structure of a process would look like this. Okay, say process PI. So this is the critical section, right? Before it, there will be something called an entry section, where possibly PI will check whether someone else is in the critical section, etc. Or it will give an indication that I'm going to enter my critical section. Right? So that is the entry section. And after the critical section, there is usually an exit section. Where again, what do you think is the purpose of the exit section? What do you think PI should do roughly in the, like intuitively? What should PI do in the exit section? Yeah, so basically, okay, Shubham, yeah, notify other waiting processes is like sure that then PI has to know which other processes are waiting. So yeah, logically you are correct, but basically, yeah. So what Ayud said, like a simpler version is that what Ayud or Mayank said, in the exit section, PI should at least indicate that it has completed executing the critical section. Okay, so in the entry section, PI should check if someone else is in the critical section. If not, it should indicate in that I am going to start my critical section. That is the purpose of the entry section. And in the exit section, PI should indicate that I am done executing my critical section. So that other processes can execute their critical section and so on. And the rest of the program is called the remainder section. Okay. So this is the main distinction of the program. Critical section is the part which we want to guard. And therefore something needs to be done before it and something needs to be done after it. Okay. Now, there are several different solutions to critical section problem, among which we will discuss a few. Okay, Akshat has a question. Wouldn't it be easier to lock and release allotted shared memory than blocking all other processes for critical state? Wouldn't it be easier to lock and release allotted shared memory? Okay, so I'm not, so Akshat, maybe you can maybe unmute yourself and clarify. Uh, I'm not sure of this question. What do you mean by lock and release allotted shared memory?
Uh, so like we are blocking every other process to use that shared memory, right? So just lock the shared memory, and no other process can access that. And when the process wants to release it, then others can access. Right?
So basically, what you are telling is one way of addressing the critical section problem.
Yes, like we can block that specific shared memory, right? We don't have to block all other processes waiting for some other thing, some
No,
other
so oh,
memory.
wait. Why are you thinking that one process will block every other process? So see again, let me go back. See, we are considering this set of system of n processes. This is not all processes in the system. These are the set of processes which are cooperating. That means which are actually using the same shared memory, etc. Right. So there is no, of course, there is no like reason to think that one process will block all other processes in the system. Maybe, I mean, this language could have been a bit better, but we are only talking about those processes which are using the same shared memory. Those are the competing processes.
Okay. Yes.
Okay. So, I mean, what you are telling is one of the intuitive solutions. Like once one particular process, a PI, when it tries to access those shared memories, the other processes which are also accessing that shared memory should be kind of blocked. So you can intuitively think of this as locking that shared memory. And of course, this will have no effect on completely different processes which have nothing to do with this shared memory. Okay. Okay, which has another question I see. Is it possible for a user process to define the critical section? If yes, isn't there a threat that it can hijack the full processor time by defining a large critical section? Very good question. This is exactly why I said that we will not go for such restrictions, that as long as a process is in a critical section, we will not allow any context switch, etc. Then exactly what which pointed out that can happen. A kind of malicious process can declare a large critical section and say that let's hijack the whole process at time. But here understand that we are not going to interfere with the multiprogramming part. That means context switches will happen as decided by the timer, etc. Right. So one process will not be allowed to get all the CPU time. Yes, you might say that one process can prevent other cooperating processes from accessing the shared memory. Yes, but again, see, that is why it's assumed that they are cooperating processes. It's not assumed that one of them will try to hijack everything and prevent other processes from accessing the shared memory. Right. So we are talking about cooperating processes. And of course, your first question, definitely, it is possible for a user process to define the critical section. I mean, in one of the lab assignments, you will do it. So yeah, I mean, that's the whole idea. Of course, kernel processes also have critical sections, but definitely user processes can have them because it's a very common situation that multiple processes need to cooperate and update a shared memory, etc. Okay, and Rahul has a question. Even among processes that share memory, can we execute processes that do something that is not related to memory? Of course. So Rahul, let me ask. Okay, Rahul has a good question. So what do you think is others? What do you think is the answer to Rahul's question? Even among processes that shared memory. So there are say n processes which are sharing a particular memory, and one process is executing in the critical section. Can the other processes do something that is not related to the shared memory? What do the others think? Okay, and yeah, okay, most of you feel yes, which is good, yes. And in the slide that I am showing now, actually, is that question answered? Kind of. in this slide. In this slide, there is something which is one term I'm looking for. Exactly what Shubham said, the remainder section. So if the other processes are in the remainder section, then there is no harm at all. Only restriction is that more than one process should not be in the critical section. Otherwise, all processes can execute remainder section concurrently. I mean, clearly this remainder section is not something which has to do with the shared variables. This may be just taking some input from the user, writing something to a file which is not shared, whatever. So we are not worried about what processes are doing in the remainder section. Only point of contention is the critical section. So as long as it is as long as two processes are not in the critical section, we are fine. They can be in the remainder sections. Okay. So now there are different solutions to the critical section problem, and we will discuss some of them. But any feasible solution should give some guarantees. Right. So a correct solution to the critical section problem must satisfy these conditions. First, mutual exclusion. So this is what we have been discussing till now. If process PI is executing in its critical section, no other process should be executing in their critical sections, even if PI is not assigned the CPU at this point of time. Okay. Okay. Next requirement is progress. I see a question, but I'll come back to it. Next situation, next condition is the progress. If no process is executing in its critical section right now, and there exists some process that wishes to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. Okay. What does this intuitively mean? So suppose there is no process currently executing in the critical section, but there are some processes which are wanting to enter their critical section. Then the design should not be such that those processes have to wait indefinitely. Since there is no process currently executing in its critical section, others should not be made to wait indefinitely. Right. When can this happen? That some I mean, what can be a bad situation? How can so when can this requirement be unfulfilled? As in, no process is executing in its critical section, but some other processes are trying to enter their critical section, but they are blocked. When can this happen? Like, it should not happen, but what is a bad situation in which this can happen? Exactly what I would said. One bad situation where this can happen is some process forgot to do the job in the exit section. As in, the purpose of the exit section was a process should indicate that I am done with executing my critical section so that others also get a chance. But suppose some process forgot to do that. Like while writing the code, kind of it forgot, I mean, the coder forgot to indicate that it is done with its critical section. Then the situation will be that this process is not in the critical section, but because it has not notified that it is done, others also cannot enter the critical section indefinitely. That is not a correct solution. So, I mean, basically, like this is one situation where it can happen. So every process must indicate that it is done with executing the critical section. The next requirement is bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical section after a particular process has made a request to enter its critical section and before the request is granted. Okay. So suppose a process PI has made a request to enter its critical section and it is currently waiting. So it should not be made to wait indefinitely or unboundedly. So it should not be that say PI has made a request to enter its critical section. But before PI's request is granted, all other processes are repeatedly being given access to critical section. Right? So this is a situation where PI will starve. Right? So PI has made the request, but all other processes are getting priority over PI. PI is not getting a chance to enter the critical section. This is not a good or correct solution. So no process should starve. Right? Of course, there is an assumption here that each process executes at a non-zero speed. Assume that each process executes at a non-zero speed, and there is no assumption concerning relative speed of the end processes. Like in some theoretical situation, it can happen that say one process has a very small critical section and another process has a very big critical section. Maybe they both share a big table, but one process has to update every entry of that table. Another process has just to read one entry from that table. So in that case, it can happen that that process which requires a large time in its critical section, that may have to be given priority, and the other process may have to wait for a long time in order to access its critical section. But yeah, I mean, those things are not considered here. So no assumption concerning relative speed of the end processes. Okay. Okay. Yeah, I'll stop here. I mean, I won't cover the other slides, but I see a couple of questions, so let me just answer them. Okay. Okay. First of all, Rahul had a doubt or something, but the process has to wait for the process that is in critical section to indicate that it's done. Okay. So Rahul, has your doubt already been answered? If not, please unmute yourself and say.
Sir, so like I had the doubt that the process that is waiting for to enter in the critical section is like still waiting for the other process.
Of course. So, I mean, as long as one process is in its critical section, other processes have to wait if they want to enter the critical section. So what's so again, I'm not sure about the doubt.
So, sir, I'm actually talking about that the remainder section is written below the while loop. But what if the other process wants to execute something before entering the critical section? Like that's not related to the shared memory.
Okay, fine. So you are telling that, I mean, okay, is your question that there can be something even before the entry section?
Yes, sir.
Yeah, sure, it can be. Yeah, I mean, that's not shown in this picture, but clearly, I mean, there can be things before the entry section. I mean, here as as in they are just grouped into the remainder section. So yeah, I mean, yeah, depending on how you write your code, I mean, steps which are not related to this shared memory can be even come before the entry section, etc.
Okay,
Fine?
thank you, sir.
Okay. And Tanmay has a question. Suppose two processes have critical section, but they don't share the same memory. So can they run both in the critical section? Again, okay, Tanmay, again, let me repeat. In this whole chapter, we are going to discuss cooperating processes which are accessing the same shared memory, let's say, or the same shared file or something that they are doing together. Right. So if you are talking about two processes that are not sharing the same memory at all, then they are not a set of cooperating processes. Okay, so let me make this point very clear to everyone. In this whole chapter, we are considering processes which are accessing some shared variable or some shared file or some shared resource together. That is why they are cooperating processes. If they are not cooperating, or if they do not have any shared variable at all, then I mean, it's not even under the purview of this chapter. There is no need for synchronization at all. Okay. So any other questions? Okay, Akshat has a question. Suppose a process needs to take input and takes up critical state and the process that writes to the shared memory gets control later. Wait. Okay, maybe unmute yourself, Akshat. A process needs to take input. Okay, so first of all, I mean, again, sure, you can write programs like that, but critical section is not the place to take input. Why do you think input would be taken in a critical section? A critical section, intuitively, I hope you understand that critical section should be as small as possible, and it should only be used to modify shared variables, etc. So maybe you can write such a program, but why maybe? Of course, you can write such a program, but the idea of critical section is not to take user input or do I/O. Unless, of course, the I/O is to a shared file, etc. So again, I'm not very clear about what you are asking. So maybe unmute yourself and ask. Yeah, fine. OK, yeah. So of course, you are free to write your own code, but critical section is only meant for doing something which is some steps which are critical and on the shared memory. So typically taking inputs, etc. is not encouraged in a critical section. OK, any other questions? No? OK, in that case, I have a one question not related to the matter, but so tomorrow 9 to 10 is the exam, fine. So maybe, OK, one person, maybe unmute yourself, someone. OK, let's say. OK, Dhrumil, can you unmute yourself?
Yes, sir.
Yeah, so tomorrow 9 to 10 is the exam, fine. What is the schedule of the class after 10?
Sir, actually, I don't have a class after 10.
But some people do, like.
I'm not sure if somebody.
Yeah, so that's why, OK, fine. That's what I'm asking. Like, let's say 10:30 to 11:30, etc. Do many people have classes then? The reason I'm asking is as follows. We missed the class yesterday, so I am going to record the lecture, fine. But this is a tricky chapter, right? So I would like to record it at a point where if you want, you can join. So like tomorrow, if I say record it at 10:30 to 11:30, then it's not a compulsory class, as in I'll record it and you can check the recording later. But I'll record the lecture at 10:30 to 11:30 tomorrow. If you want, you can join. I'm specifically asking this or suggesting this because this chapter is a bit tricky, as you see, you had lots of questions today, which is quite normal, as in process synchronization can be a bit confusing. Fine, so I'll just announce, maybe I'll pick a time tomorrow around say 10:30, 11:30 or something like that. There is lab submission tomorrow at 2 p.m. Okay, yeah, I can understand. And so it's the like critical section right before 2 p.m. I can understand that. Fine, but again, as I said, I'm not, I'm not making it compulsory to attend the class. I'm just saying that I'll record the lecture tomorrow, say at that time. It's fine if no one joins. I'll just keep it recorded. You can check the lecture later. If you can join, do, because this chapter is a bit tricky, as you understand, as you might have understood today. Fine, I'll put up an announcement on Teams that I'll be recording at this particular time tomorrow. Okay, it will be after the test, of course. Okay then, thanks. Let me end the class today. Thank you, everyone.